Good evening everyone, my name is K. Dinesh. I am from Civil Engineer second year. Is here to present my topic on elementary calculation of energy consumption and power factor improvement. These are the two parts which we are going to discuss in this presentation. The first part is about energy consumption and electricity bill, and the second part is all about how to improve the power factor. What are the methods to improve the power factor? Starting from the basic definition of electrical energy consumption is defined as the electrical energy is defined as the product of power and time, where capital E is equal to P into I. We can also write this expression in terms of V and I, that is E equal to V into I into T, whose units are joules. We know that power is equal to product of voltage and current. The SI units of energy are watt, second or joules. Practically the electrical energy is expressed in watt hour or kilowatt hour. The electricity meters installed by the electrical board, which are used to measure the electricity consumption in kilowatt hour. Then when we coming to the electricity bill, monthly electricity bill is charged on the basis of monthly energy consumption in terms of number of units. Let's say that 1 unit is equal to kilowatt hour, that is equal to 1000 watt hour. The per unit rates of electricity consumption are different types of customers, such as domestic, farmers, industrial units, etc. Here's a small example problem that we can calculate the energy consumption of a system that uses 150 watts of power and operates for 4 hours a day. We know that power is equal to V into I into T, where we know the power, where we know also the time, and you can see that E is equal to 150 by 40 by 60 by 60 by 1000, where we are converting the hours into seconds. Hence the energy consumption is 2160 kilowatt hour. And coming to the second part of the presentation, the second part covers about the power factor. The basic definition for power factor is the cosine angle between the voltage and current, where coming to in this topic in terms of power, the cosine angle between voltage and current phases in an AC circuit is known as the power factor. If phi is phase angle between the voltage and current, then the power factor is cos phi. Let's take an example. Consider an inductive circuit in which current I lags the applied voltage by an angle phase phi, whose vector diagram is shown in the presentation. The current I can be resolved into two components, one in x direction and one in this y direction. The horizontal component is, which is x direction, is I cos phi, which is the phase in with voltage V. Vertical component, which is in direction of phi axis, is I sin phi, which is out of phase 90 degrees with V. The I cos phi component is known as the active or wattful component, where I sin phi component is known as the reactive or wattless component of the total current. In simple terms, we can say that reactive power, where reactive or wattless, can be known as waste power. If all the components of triangle OAB of the figure A is multiplied by the voltage, from the previous slide we have known that we have compensated the current into two components. When we multiply with V, we get the power triangle, which is shown in the figure P, where OA is equal to VI cos phi, which is also known as the active power, denoted by P, which is measured in watts or kilowatts, where AB is equal to VI sin phi, which is also known as reactive power and is measured in VAR or kilo VAR, voltage amp reading. OB is equal to VI, is also known as the apparent power, which is denoted by S and is measured in voltage ampere or kilovoltage ampere. From the power triangle OAB in figure B, By using the basic formula, hypotenuse square is equal to opposite square plus adjacent square, where OB square is equal to OA square plus AB square. We know that OB is equal to S, OA is equal to P, and AB is equal to Q. Substituting that, S square is equal to P square plus Q square. We can write in terms of units, where kilowatt A square is equal to kilowatt square plus kilowatt A R square. The power factor formula is given by the power factor in AC circuit. Cos phi is equal to VI cos phi divided by VI, that is equal to kilowatt by kilowatt ampere, which is in terms of, we can say that active power, the ratio between active power and apparent power, is also known as the power factor. The power factor of the circuit also be defined as the ratio of power factor and the apparent factor, where we can calculate the reactive power kVAR is equal to apparent power into sin phi. The advantages of power factor is, the first advantages is the kilowatt capacity of the prime mover is better utilized. The kVA, kilowatt ampere capacitor of the alternator, transformer and transmission lines is increased. There is a reduction in transition line losses. The voltage drop in the transmission line decreases, which results in better regulation. The efficiency of every plant is increased. The overall cost per unit decreases. Where we know that to improve the power factor, there are three methods. The first method is static capacitor. The second method is synchronous condenser. The third one is phasor advancer. Starting from the static capacitor, the power factor can be improved by connecting the static capacitor in parallel with the equipment operating at lagging power factor. We are actually connecting a capacitor with parallel to the equipment operator, so that we can nullify the current, because the operating equipment consists of lagging current, where when we place capacitor parallel to the equipment, it produces lead current, which nullifies the whole current. The capacitor draws leading current from the supply voltage by 90 degrees and compensates for the lagging current, reactive components of the load current. In the case of three-phase, the capacitor can be connected either in star or delta as shown in the figure. The advantages of static capacitor is they have small losses, where the energy loss is very minor or negligible, requires less maintenance, where the higher efficiency is there, low cost, easy to install. Coming to disadvantages of static capacitor: short service life, and it is uneconomical for repairing work, easily damaged due to the overload voltage. Second part is synchronous condenser. An overexcited synchronous motor running on no load is known as the synchronous condenser. In easy words, we can say the synchronous motor runs on no load principle. The overall excited synchronous motor takes the leading current and behaves like a capacitor itself. In the first case, we need to place a capacitor parallel to the equipment. In this case, synchronous condenser itself behaves like a capacitor, which draws leading current and nullifies the lagging current. When it is connected across, the supply draws leading current partially or fully, compensates for the lagging reactive components of the load current, and thereby improves the power factor. Here's the figure where the synchronous condenser is connected to a three-phase load equipment. The advantage of synchronous condenser is it can withstand overloads for a short duration. By varying the field excitation of the synchronous condenser, the power factor can be improved to a final value. Coming to the disadvantages, cost is higher than the capacitor, and we have a high maintenance, low efficiency as well, produces noise during operation because it works on the motor principle. And the last method is phase advancer. The phase advancer are mainly used to improve the power factor of the induction motor. We can say this phase and advancer is merely works for the induction motor. The induction motor actually draws an exciting current that lags the voltage by 90 degrees. We connect this phase advancer to produce leading current to fall in the power factor of the induction motor. The power factor can be improved by the phase advancer which supply an AC exciter. It is as similar as the previous one, synchronous condenser. The phase advancer supplies exciting amperes turn to the rotor circuit at slip frequency. The phase advancer is mounted on the same shaft as the main motor by supplying more ampere turns from the phase advancer. The induction motor can be made to operate at a leading power factor like an overload excited synchronous motor. And the advantages of phase advancer is the lagging kVA kilo voltage ampere reading draws by the induction motor can be considerably reduced by supplying leading ampere turns at slip frequency. The phase advancer is conveniently employed with the use synchronous condenser is not suitable. Especially we use this phase advantage for induction motors. The main disadvantage of phase advancer is they are not economical for motors below 150 kilowatts. Here ends my presentation. Thank you for listening.